So today I am going to start a new chapter named as Internal Symmetries. This is a new chapter, and under this chapter this is the first topic which I am going to discuss in this lecture. It is selection rules and globally conserved quantum numbers. So first of all, let me talk about a brief introduction to it. So a particle, let us consider a particle, and a particle decay into two or more lighter particles if it is allowed by energy momentum conservation, Now a question arises that why a particle decay into two or more lighter particles. So to answer this question, let us talk about entropy. So entropy is basically Boltzmann constant, natural log of phase space, right? So when a particle split into more than one particles, what will happen? The entropy tends to increase. Means entropy of smaller particles tends to increase, right? That's what will happen. So that means what this suggests? This suggests that increase in entropy tends to decay particles, and this keep on decaying. But particles not always keep on decaying, but this process will be stopped. So that means what stop it? What stop this decaying? So this suggests that there are some selection rules which forbid the decay, this decay. Another important thing which we have to keep in mind, there are some decay processes. There are some decay processes which are allowed by energy and momentum conservation. Energy and momentum conservation, but do not take place. So what does it mean? It means that there is something else other than the energy and momentum conservation, and which is necessary to judge whether the process will take place or not. So that means there must be some selection rules or conservation laws which forbid these decay. Right? So we call these laws as global conservation laws. Global conservation laws, right? And let us discuss these one by one. So first of all, first is the electric charge conservation. Electric charge conservation we understand these laws by taking certain examples. So consider a decay process. That an electron decays to neutrino and gamma ray. So let us assume that this process follows energy and momentum conservation law, but even then this decay process cannot be observed. This decay process cannot be absorbed. So why this process will not happen in nature? The reason is that in this process that the charge is not conserved. That the charge is not conserved, right? So charge is said to be conserved. First of all, let me talk about what is the meaning of conservation of charge. So the charge is said to be conserved. Charge is said to be conserved if delta Q, and delta Q means QF minus QI. This is the charge of the initial particles, and this is the final particle which are produced after the decay, and these are the initial particles, right? And it must be equal to 0. If this will happen, then we can say that the charge is conserved, otherwise charge is not conserved. So let us talk about this. So here the charge will be -1, here the charge will be 0, here will also be 0. So in this side overall charge will be 0. So that means this charge is not equal to this charge. That means this process will not occur. So therefore for this reaction delta Q will be equal to 0 minus -1. This is equal to +1, and this is not equal to 0. So I can say that the charge is not conserved, right? So charge is not conserved. That means that the process is not feasible or the possible. The process is not possible. So this is the one thing which I have discussed. Now another one is the baryon charge or baryon number conservation. Another is the baryon charge, or baryon number conservation. conservation. So I will talk about variant charge and the variant number conservation later on in detail, but here I will take some example and I will discuss its necessity to explain certain processes, right? So consider some decay processes. So these are the two decay processes. A proton decays to positron along with a gamma ray photon, and another process is proton decays to E positive plus the neutral pion. These are the two things which I am considering. So first of all, let me talk about the charge. So if you talk about charge, then the plus 1 is the charge over it, plus 1 here. So in this case the total charge will be conserved, and in this case the plus 1 is the charge over the proton and plus 1 for the positron, and the pi meson has the 0 charge. So in this case also the charge will be conserved. But that so that means on the basis of charge conservation, these processes may be possible, but we cannot see these experimentally. So that means other than charge there is some another thing which is not conserved, and that is the baryon charge. So that means we will assign a new number and we call that as baryon number, right? And if this baryon number is also conserved, then we can say that the process is feasible, otherwise it's not. So let me talk about the values which this B can take. So B may have plus 1 value, minus 1 or the 0. So plus 1 for baryons and minus 1 for antibaryons and 0 for the leptons and mesons. So again consider the same reactions, the reaction which I have considered in the beginning, that proton decays to E positive and the gamma ray photon. And if you talk about the B, the plus 1 is for proton, 0 for positron and 0 for gamma ray. And another reaction which we have chosen is E positive to pi naught. So here the baryon number is plus 1 for it, 0 for it and 0 for it. So a baryon number is a additive property, and if a baryon number is conserved, then we can say that process is feasible, right? Feasible, that is delta B must be equal to BF minus BI must be equal to 0. So if I try to look at this case, so here delta B is what? Here delta B is equal to basically 0 minus plus 1, it is equal to minus 1, and in this case also that delta B is equal to 0, minus minus plus 1 is equal to minus 1. So this is not equal to 0, this is also not equal to 0. So that means these two processes are not possible. Means the baryon number is not conserved. Therefore processes are not possible. Processes are not possible, right? Then another important parameter is the lepton number or the lepton charge conservation. Means the lepton number or lepton charge conservation. There is another very important thing. So again, consider a decay process. The decay process is that antineutrino of electron plus a nuclei having Z charge and A is the mass number, it decays to Z plus 1 A plus electron will also be emitted. So in this process again charge is conserved. Charge is conserved, but the process is not allowed, right? The reason is that the lepton number is not conserved. Number is not conserved. So let us talk about lepton number conservation. Means lepton number conservation means the delta L must be equal to LF minus Li, it must be equal to 0. This is the meaning of it, right? And let us assign the few values to it. L is equal to either plus 1, minus 1 or 0. Plus 1 for leptons and minus 1 for anti-leptons, and this is for other particles. We will talk about these lists in later on. In this lecture I just want to show you that how these quantum numbers global quantum numbers are important, right? So let us understand this with the help of some examples. So let us consider few examples. So neutron decays to proton plus electron plus antineutrino. Check whether the lepton number is conserved or not. So L is equal to 0 for this, 0 for here, 1 for here, and minus 1 for here. So that means in this case the lepton number is also 0, here is also 0. So therefore delta L is equal to 0 minus 0 is equal to 0. So what does it mean? Means change in the lepton number during this process is 0. So that means the process is allowed. Process is allowed. Let us take another example. What was that? That antineutrino of electron plus a nuclei having charge Z plus 1A is the new nuclei which we are getting, and this is electron will also be emitted. So here it is minus 1, it is 0, it is 0, and it is 1. So these are the lepton number assigned to these, right? So if I talk about delta L is equal to LF minus Li, so here the lepton number is 1 minus 1, it is 2 and it is not equal to 0. So that means it is not equal to 0, so that means process is not allowed, because lepton number is not conserved in this case. Let us take another more example. And it is antineutrino of electron plus Za gives us Z minus 1A, and it is a positron. So if we try to look at it, it has the minus 1 lepton number, and it has 0, it has 0, and it has minus 1 also. So if we talk about delta L for this reaction, so for this delta L is equal to LF minus Li, it is minus 1 minus minus 1, it is equal to 0. So that means process is allowed, means the process is allowed. Process is allowed, right? So these are the few examples about which I talked about here. Now let me talk about the another important aspect. I am not going to discuss that here, but just talk about that. So that is the strangeness and hyper charge. Strangeness and hyper charge. So I will not talk about these here, but in the later lecture I will talk about. But for some process to take place, strangeness denoted by S and hypercharge must be conserved, and it is denoted by Y must be conserved, right? So here in this lecture I talked about globally conserved quantum numbers, and those are the charge conservation, lepton number conservation, baryon conservation, strangeness conservation, and hypercharge conservation, right? So that's all for this lecture.